So hello everyone. Today I will give a brief introduction about our SPHinXsys code. I will not go to the technical detail, and briefly I will show some results we have got with this library, and I hope with these results you can find something you are interested in, and maybe in the future you can join us and also have your own project by using this library. So this is outline. First of all, I will talk about the SPHinXsys library. This is the algorithm we are using. For example, we're using the Riemann-based weakly compressor SPH for the fluid. And we also have some multi-phase extensions. And for the solid dynamics, we are using the total Lagrangian SPH method. And we also have some results for the fluid structure coupling. And we also implemented the GPU acceleration. But I think that this part is not released. So then I will talk about the pre-processing tools for the library. And also I will show some results for the coupling with SymBody, and also the modeling of the wave interaction with the oscillating wave 30 convert. Then I will briefly show some results about the cardiac modeling. So why we chose SPH method? Actually, someone of you may not know the SPH method. SPH method is a Lagrangian particle method. It uses particles which can carry mass, momentum, and hydrodynamic property. For example, pressure, temperature, and internal energy. For discrete system, and the interaction of the particle is determined by a kernel function. This is a basic shape of a kernel function. It has a cutoff. For example, if this particle is located at this, and all the particles located at this domain will be interacted with this particle. And as a Lagrangian particle method, SPH have some advantages. For example, it can easily treat the complex free surface and also the material surface. And then it can it has shown advantage for treat the larger deformation for the fluid, for the solid. For example, the fracture of the solid structure. Also, identifying free surface and the moving interface is very easy for SPH method. And all these features make SPH method a very good choice for modeling the multi-physics system. For example, the one we are very interested in, the cardiac modeling. So this is a brief introduction of the SPHinXsys. It is an open release library under the Apache license version 2. And it is totally based on SPH, meaning that we are using the unified SPH method for modeling multi-physics system. And we have released more than 30 cases ranging from fluid dynamics, multi-phase flow, solid mechanics, fluid structure interaction, and thermal and mass diffusion, and also reaction diffusion, also the passive and active cardiac mechanics. And also, we are focused on the developing of multi-resolution, both in time and for time stepping, and also the spatial discretization to optimize the computational efficiency. So then I will briefly show some results by using the SPHinXsys. This is the results and benchmark test for free surface flow, the dam break. And this is the simulation results, and this is experimental. As you can see here, by using the SPH method, all the features for the variant free surface flow, for example, a very large run up and some break up of the free surface, also the re-entry of the free surface can well captured. And we also show here the elevation of the free surface and the capture of the pressure signals. And we can see here for this data, SPH method have a good agreement with the experimental. And here we also show the simulation for the multi-phase flow of oscillation. Here, the liquid is water, and we also have the air here, as you can see here in the meshless SPHinXsys method. As you can see here, SPHinXsys method can actually predict the interface of the air and the water. Also, it can accurately predict the impact pressure of the water. Here is our extension work based on the multi-phase flow. We have developed a multi-resolution multi-phase solver, also in SPHinXsys, and this is the Dunn-Bracket flow. And we also introduced the surface tension, also in multi-resolution scenario. Then we can go to the solid mechanics. We know that in solid mechanics, there was some very developed method, for example, FEM. However, we also can see that for some very large deformation benchmark test, SPHinXsys method can also accurately predict the deformation of the structure. And we also compare the results of SPHinXsys method with some traditional method. We can see here, SPHinXsys method can accurately predict the deformation. And we also have developed the contact model for the interaction of, for example, a solid structure with an elastic structure with a wall, and also some compression of a cubic muscle. Within this contact model, we can do a lot of, for example, applications in bare engineering. Also, services can do some fluid structure interaction. And this is a benchmark test for the fluid structure interaction. We have a cylinder here, and then it is attached by an elastic beam. And when interacting with the inflow, the beam will oscillating during the interaction. And we also show the position of the free end of the beam, and we also compare our results with some immersive boundary method. We can see here, SPHinXsys method show very good results. Also, we have developed
short question.
Okay.
If you compare the computational efficiency compared to a traditional mesh solver, how is it? If you compare.
Okay, I will show you later. Okay.
Okay. Thank you.
Okay, we also develop a processing tool in our library. We know that if you are using a mesh-based method, you have to draw your mesh using some also pre-processing tool. For particle method, we have to create the initial condition for the particle distribution. Actually, generally there are two approaches for particle generator. One is based on put the particles on the lattice. Another is based on convert volume element mesh to the distribution of a particle here. As you can see here, for this method, we have isentropic particle distribution. However, we cannot accurately represent the complex geometry. For this method, we can have a accurate representation of the geometry. However, as we just convert each element to a particle and then give the element volume to the particle volume, we cannot get an isentropic distribution of the volume distribution. Therefore, we have developed a CAD-compatible body-fitted particle generator. The basic idea is we read the CAD geometry and then construct a level set function based on the representation of the geometry. And then we will relax the particle distribution using some physics relaxation, also with the surface constraint. Then we can get the body fitted particle distribution with the isentropic distribution for some complex structure. For example, the propeller, the heart model, and also some stand structure. With this pre-processing tool, we can extend the SPHinXsys library to some engineering applications. So this is one important application of SPHinXsys is hard modeling. We know that hard modeling is a typical multi-phase system. It consists of the conduction system, the WAF system, and also the myocardium, also the hemodynamics. So if we are using the unified SPH method for this modeling, we can easily deal with the interface of the different server systems. And until now, we have some very compromising results for the simulation of the electrophysiology. This is the generation of the spiral wave on square geometry and also on the circular geometry. And we compare our results with some traditional Bayesian method. As you can see here, the SPH method can accurately predict the spiral wave. Also, we have to some electromechanics. Here, we are using the biventricle hard model, and this is the hard deformation by using the electromechanics, and we also create a screw wave on this biventricle hard model. And then, as you can see here, for the conduction system, actually it's not diffused on the tissue. It will start on the PKG network and then go to the tissue. So we also developed a PKG network by using the reduced SPH model, and then in this case, the transmembrane potential will start conducting on the network and then distributed to the left ventricle heart, as you can show here, under the interaction of the coupling of the PKG network with the left ventricle. We can also have the deformation of the tissue. And then we're also coupling SPHinXsys with the SimBody. Actually, SimBody is a multi-body physics library, and it can handle complex multi-body modeling, as this is the result for human learning. And it's very easier for coupling SPHinXsys with SimBody because it provides object-oriented C+ API, and we just provide some inputs to the SimBody for solving the Newtonian equation, and then we have some new stage of the solid body, and then we can update the particles information in SPHinXsys. Here is results by coupling SPHinXsys with SimBody. We have a fish and we have some inflow, and if we steering the head fish with a fixed point, and then we, as you can see here, this is the experimental, and we have a half cylinder here to generate a wick, and then this is the numerical results. As you can see here, during the deformation of the fish, it can extract or harvest some energy from the flow, and then swimming forward. As you can see here, we successfully simulated these results. So then another important application of SPHinXsys is the simulation of the wave interaction with the structure. Here we simulated the wave interaction with a wave energy convert, oscillating wave surge convert. This is a basic type of the wave energy convert. And by using our pre-processing tool, we can directly read the CAD file for the wave tank and also for the flap. This is the geometry, and then we can create the particle distribution. This is the simulation results and the numerical of the wave interaction with the oscillating wave surge convert. As you can see here, during the interaction, actually the flap have a very violent rotation during the interaction of the wave with the structure. Here, this is the numerical experimental results. And then we compare some data with experimental, for example, the flap rotation and also the wave elevation. As you can see here, the SPHinXsys can accurately predict not only the flap rotation, but also the wave elevation. Also, we also compare the wave loading on the flap by compare the results of the SPHinXsys with the experimental data. You can see here, SPHinXsys can accurately predict the basic feature of the pressure signals. So another important thing is the computational efficiency. In the modeling of the wave interaction with the oscillating converge, we compare our CPU times with some SPH code, and also the Fluent, the commercial software package. This is the CPU time for per hour CPU time for 1 second physical simulation for 1 million particles. As you can see here, for the commercial software, for example, Fluent, it requires almost 60 hours for 1 second physical simulation for example, 1 million cells. However, for SPHinXsys, we only require 3.6 CPU hour times for 1 second physical simulation, and for 1 million particles. We can see here, in this simulation, we do not use the GPU acceleration, only with the CPU. So it means that if we run the simulation for 2 million particles and for about the 13 seconds physical time, it only requires 8 hours. It means that so you have a coding work for the whole day, and then you go home. Before you go home, you just send your simulation work to your desktop, and then the next morning you can see the results. Okay, you may already have the link to the library, and I hope you can find something you are interested in and find your own project based on this library. Okay, thank you. That's all. If you have any question, so please ask.
I have a single question. What kind of experience do we need to have, prior experience do we need to have with such computations, like numerical computation using software?
Sorry, experience?
Yeah, prior experience.
I think if you have some basic knowledge of C++ and some basic knowledge of the computational fluid dynamics, or better on SPH, you can do your own simulation. I think it's not a difficult task to start with the simulation. You can learn the fundamental theory of particle, and then you can run the simulation by your own self.
No, we don't need that high level if we don't want to contribute the code. We use this one just for practice in our class. Is simple because we will provide some template, and what you need to do is just copy some template, do a small modification. We are able to do simulation. But if you want to contribute that, certainly you'll need more background on that. But if you want, we only use this for this numerical modeling, small project in our course would be not much. Yeah.
Also, actually, I forgot the question. I had another question, but I just forgot it.
One question. Would it be possible to simulate reactive flows using this particle hydrodynamics method?
Yeah, it's possible. We already have the reaction model in our library.
Okay. Do you include another library for that, or which library are you using for that?
You mean for the reaction?
Or Cantera, or what are you using for the chemical reactions? Which library is implemented?
No, we developed the reaction algorithm by ourselves.
Okay, I understand.
Mm-hmm.
Yeah, I remembered. I just wanted to ask, are we going to have tutorials regarding this software, or should we get familiar with it ourselves?
We have tutorial. If you go to the website, we have a tutorial.
You mean if we have some class level tutorial is
Class level.
I think we will arrange.
Yeah, we hope so.
Yeah, but on the website we have already the tutorial, and we are making more. Could you show him the website? Or?
Okay, I will stop sharing. It's a little bit slow. So this is the website. Its name is SPHinXsys.org, and you can have the source code link to the GitHub. Also have a documentation, and yeah, also some tutorial here. You can have, now we have some, we have the installation overview and of first example of the it's a 2D dam brick, and also example of the elastic watch. And now we are adding more examples in this tutorial. And also you can have some, for example, the basic theory, structure overview, and the multi-resolution modeling kind of, and also some basic theory concerning the SPH method. Yeah. Okay, that's all. Any other question?
I think it's if you have any question on the requirement, could you send an email to me or Dr. Chi, or you post your things on Moodle. That's all okay. And then we consider what you asked. Probably we will have more tutorial in class, or probably for example, probably have a. I think that there's another tutor. I think Mr. Dong will help you probably to construct the cases in the class as like in the exercise time. So probably you can by hand practice with, for example, the first project we would like to consider to simulate a channel flow. So Mr. Dong, Mr. Wu will try to instruct hand by hand. Then you can do it in the class. Yeah, that will be make sense easier. And anyway, you have an extra requirement. Could you just send an email to me, or then we can check it. Mm-hmm.
And one question: if you have problems regarding the installation, who can we contact?
You also ask Mr. Wu. I will be good. Mm-hmm.
Mr. Wu. Okay. Okay. Thank you.
Yeah. Mr. Dong Wu will do it. So I think you got his email.
I will look in the course description. Maybe it's there.
He's one of the tutors, and you can. Mm-hmm.
Okay. Thank you.
Yeah. Yeah. Okay. Oh, still one question. Oh, yeah. Okay. Okay. So we still keep like several minutes here for the Zoom, and we can finish if you don't have anything. Then we finish this class, and maybe if anyone have still some question, then they can stay and ask. Okay. Okay. Bye bye.
咋了？你进来，你就在这说吧。没事吧？现在就可以说吧。
嗯哼。
哎，胡老师，玉姐好像有事跟你说。
Thanks. Bye.
啊，就是
什么事儿？
这个啊。
第3，我是那个考试那个查卷子是吧？
对。
怎么样？
还是有点问题。然后就是有个学生，他 就是他可能过程写了，但是呢，就是过程呢，因为他整个的分是7分嘛，然后有个学生，然后他过程写对了，然后就给了他2分，然后他结果都是错的，所以就给了他2分，然后他不愿意，然后就跟我们 argue 了半天。然后我说我一会儿要不下午再找个时间商量一下怎么弄，胡老师。
OK，那就是那一个人，其他人呢有没有变呢？
有变的，其他人总共有3个吧，加上他总共3个人需要变，但是还不知道就是最后成绩有没有变，反正是现在基本上有一个加了0.5分，有一个加了1分，然后这个呢就是说最多给他就是张文斌的意思是最多给他加1分，但是他不愿意，他想可能多加点，所以还比较。
问题是他多加点能不能够升级？就是他现在多少分？
我这个还没有 check，因为他那个分好像在那个梅尔那儿，他在他那儿呢，所以我没有看。
因为那个 Excel 上面有啊。
就是那个 To Online 上有是吧？
对呀，Excel 他不发了 Excel 那个 file 给我们了吗？
他那个 Excel 我看不太懂。
那你看懂啊？
嗯，
你得看懂啊，你不能看不懂就不看。你用 Excel 导进去就可以看懂了，你用打开 Excel 打开来就可以看。那你看他是不是会加分？他现在是多少分？他现在多少分嘞？
他现在我没看他那个分。
那你看那个 Excel 分儿吧，确定1分以后，然后就是说最好是说不改这个分儿。
对，
给他加的话，就是说加点数倒是可以，但是如果要改分儿的话，这个那个马尔今天来了，他也来了，是他们来了，他们那边来人了吗？
他也来了。
他们那个加分没有？
他那边好像变动不大，就这一个就这一个人有点问题，就是说下午反正还有2个人，下午2个人检查完。
哦，还有2个人是吧？反正我们尽量是不改他的分了，他不生气，他不高兴，他妈考得不好，他不高兴正常噻。
对，他不高兴，然后他说他过程对了，他就中间有2个参数写错了，中间2个参数写错了嘛，然后结果是错的嘛，所以给他了2分。
一共多少分嘛？
嗯，
就是这个，就是说答案也对，过程也对，多少分？
都对的话是7分，它是2问嘛，它相当于是2个部分嘛，就是相当于是
过程都对，怎么会能错嘞？怎么回事呢？这是不是也怪怪的？
相当于是一开始的过程，它只是那个就是求解的过程是对的，但是呢，它那个参数
犯了个错，
参数是错的，所以它结果就是像第1问的结果就错了。然后呢，它那个第2问也全错了，根据第1问的第2问是根据第1问来做的。
那这个得给他点分呢，因为什么？因为他理论是搞错了嘛，是犯了个小错嘛，那你不能因为小错给他扣大分呢？一共7分呢，才得2分，太少了点。
关键这个是张文斌改的，他说他的标准就是这样，他所有人都是这样。我觉得要加的话，顶多给他加上1分，就是过程分，给他再加上1分，3分。
看他结果的成绩，他能够加一点，能够蹦一点分也可以了。但是问题是这个张文斌就是为什么呢？因为我们说他如果过程都是对的，那么只是犯了个小错，那个结果错了，这个东西不能考虑他是这样不行嘞。
行，胡老师，要不咱们下午咱们找个时间再。
张文斌的时候看看他那个这样的人大概有多少个？如果没有其他人都是错的的话，过程也错了，那就无所谓了。如果其他人也差不多，那估计你还得稍微给他调一点那些人。因为他整个东西都搞对了，然后他知道这个理论这个顺序都对了，为什么就是犯了个小错错了？那也对他来也不太公平的。
所以他不
高兴也是对的。那下午再讨论吧。
行，胡老师，下午他大概3点多到4点吧，您看怎么样
？OK，
好嘞，胡老师。
走吃饭吗？
那行，那就结束了。
结束吧。
怎么吴栋，你有什么要说的吗？
没有。
OK，那我挂了。
我可以说那个，您说那个 check 那个 moment 确实有点大，我感觉有问题。
什么？
我感觉有问题，我再看一下 code 哪里有。
那个不是0是吧？
对。
那不是0肯定不行，那地方必须得0的。
对。我再看一下，好，拜拜。
拜。